Hello, burgeoning statisticians. This is Dr. Chantel Marshall, and in this lecture we will be covering z-scores, or as I like to call this lecture, now you can compare apples to oranges, for Psychology 210 at Nevada State College. In this lecture, we will cover some things that you've already learned and combine them with some new ideas to discover what z-scores are and how they can be of use. So we'll start with an overview of the normal curve, which you've already been introduced to, but in order to conduct analysis using z-scores, we really need to rely a lot on the normal curve. We'll then review standard deviation to remind you about variability and how important standard deviation is when we talk about a specific distribution. Then we'll go on to why we want to compute z-scores, when we would use them, and how they tell us about the scores within a sample or population that we have. And then we'll move on to actually calculating the z-scores using a very simple formula that can do a lot for us. So we'll be able to calculate the raw score from the z-score as well as the z-score from a raw score. So we'll go ahead and learn both of those things, as well as comparing z-scores and raw scores to one another. So often we'll move from one distribution to another, and z-scores allow us to move from one to the other, even though their scales might be very different, even though their means and standard deviations might be very different. So again, being able to compare apples and oranges. And finally, we'll end with the z-distribution, which is a very specific distribution using z-scores and taking advantage of that normal curve. So let's remind ourselves about what a normal curve is. And I have to admit that the normal curve is one of my favorite, if not my favorite types of curves. And the reason for that is because it has a symmetrical distribution. And as we all know, symmetry is very attractive, which basically means that we have a distribution that has two sides that mirror one another. At the center of this distribution, we have the mean, which is also the greatest frequency of whatever it is the variable, or whatever variable it is that we're measuring. So remember when we were graphing frequency distribution graphs, this on the bottom is the score, and here on the y-axis we have the frequency. So on a normal distribution or normal curve, the number in the middle is the one that people score the most. And this is really important for behavioral scientists for many reasons, and we'll go into that as we learn more about scores, or about z-scores. The other part about the normal curve or distribution is that as you go to the extremes, both in the positive and the negative direction, we get smaller frequencies. And this pattern for a normal curve is going to allow us to do a lot with the distributions that we have. Now you might be thinking, well, that's great, but how many things are going to have this type of distribution? And as it turns out, a lot of psychological variables, behavioral variables, things that social scientists are interested in tend to fall on this normal curve. So things ranging from height, so most people are here about average height, and very tall people are at the extreme, so you might think of basketball players, and very short people are on the other extreme, so you might think of people with dwarfism. So the variable of height falls on the normal curve, as do other things like weight, IQ, and other measures of intelligence, things like shyness, aggression, the feeling of social support that people have. It's very interesting and very useful for us as social scientists that many of these variables fall along this distribution. And when we create new variables or new scales, we try to make it so that it falls along this distribution because it's what allows us to conduct a lot of our analyses. And so if you come up with a new scale or a new variable, if you use an operational definition that's never been used before, as we discussed early on in the class, then it's a good idea to test it to make sure that it falls along a distribution that looks a lot like this one. In addition to the normal curve, the z-score relies primarily on the idea of standard deviation. And as you recall from earlier in the course, a standard deviation is the average distance all scores are from the mean. So this gives us the idea of variability. Are the scores spread out along the variable's lowest and highest score, or are they more clustered around the mean? So it lets us know how different scores are from one another. Sometimes there will be very little difference among the scores, and sometimes there will be a lot of difference among the scores. Now, one thing that I want you to keep in mind is that standard deviation is a measure of distance, and because of that, your standard deviation is always positive. You can't have a negative distance. But when you think about it, you do have some numbers that are below the mean, so we'll have to deal with that with z-scores. But when you're calculating your standard deviation, it will always be positive. And z-scores will allow us to measure whether a score is above or below the mean. And that can be negative, as you will see. Now, when you have a high standard deviation within your sample or population, the scores are very spread out from one another, so the distance is high. When you have a low standard deviation, the scores are clustered around the mean, so you have a much narrower distribution. And you can see it when you look at the distribution, and you can also compare standard deviations to one another. So if you think about it, a distribution is made up of many scores. So let's say that I survey 100 people and I have them take an intelligence test. Those 100 scores will clearly be all over the place. Not everyone will get the exact same score. We'll have some people who score on the low end and some people who score on the very high end, but most people will be around the middle. Now, each of those people has a raw score, and we're going to represent that with X. But more importantly, each score is a certain number of standard deviations from the mean. So the ones that are closer to the mean will be within one standard deviation above or below. The ones that are very far from the mean are 2 standard deviations or more away from the mean. So this is where z-scores start to come in. We're going to start to think about this distance in terms of, or in units of, a standard deviation. Okay? So let's go back to our normal curve and review the empirical rule that allows us to do this. So as you recall, the normal curve has most of the scores in the middle and fewer scores near the extreme, as well as being symmetrical. So as you remember, the middle is our mean. And what we know about a normal distribution is that within certain standard deviations, a certain population of your sample, or a certain percentage of your sample or population will be within those numbers. So what we know is that between your mean, whatever that happens to be, and 1 standard deviation away, whatever that happens to be, you have 34% of your participants or survey takers or people that you're studying, right? So we have 34% here and 34% here. So the majority of your sample or population, 68%, are going to fall between 1 standard deviation below and 1 standard deviation above, no matter what your standard deviation is. Now, just a second ago, I told you standard deviations can't be negative, right? And you're thinking, oh, but there's a negative number here. I'm not saying that the standard deviation itself is negative. I'm just saying that 1 standard deviation below our mean, whatever that happens to be, will include 34% of that sample or population. And as we get further away, we have fewer and fewer people out to the extremes. So on this distribution, only 2% of our population will have a standard deviation, or will be more than 2 standard deviations away from the mean. So let's think of an example. There is an actual society out in the world that's called Mensa. And Mensa is a society solely for people who have taken an intelligence test and scored very high. Specifically, they want you to have scored at least 2 standard deviations or more away from the mean of that particular test. So let's say that I want to apply to be a part of Mensa. And for those of you who speak Spanish, you might realize that it's a little ironic that it's called Mensa because in Spanish that word means dumb, literally. But for whatever reason, they have called themselves Mensa. And let's say that I would like to join. So I take the International Smarty Test, which I'm pretty sure does not exist, and I score 34. I have no idea, just looking at the raw score, whether that's going to get me into Mensa. I have to also look at the mean and the standard deviation. So let's find out. If I get a 34 on this particular test, then I still need to know the mean and the standard deviation before I can know if I qualify for Mensa. And the reason that Mensa has this, you have to have more than 2 standard deviations away from the mean score, is because there are many, many intelligence tests out there. And so they don't want to have to go through the trouble of trying to figure out for each test, including new ones that come out all the time, what the minimum cutoff is. Instead, they simply say, whatever your test's 2 standard deviations away score is, that's what we're going to use. So if I score 34, and this particular test has a mean of 26 and a standard deviation of 4, then let's find out. So the mean would be 34, or sorry, the mean would be 26. 1 standard deviation away would be 30. And 2 standard deviations away would be 34. So my score would fall just at the cutoff point of 2 standard deviations away, and I would qualify. But let's say that instead of having a mean of 26 and a standard deviation of 4, this particular test has instead a mean of 40 and a standard deviation of 6. So now the mean is 40 and 1 standard deviation below is 34. So now, even though my score, raw score, hasn't changed, where it falls in terms of standard deviations has changed dramatically because of the different mean and different standard deviation. So in this case, my score would fall at -1 standard deviations away, and that would definitely mean that I do not qualify for Mensa. So this idea of being able to take a score and quantify it in terms of how many standard deviations away it is from our mean is the heart of a z-score. And it's what allows us to compare different measures of the same variable, even though they can be very different in the means that they have, how much variability they have, and all of that good stuff. So let's get into what a z-score is so that we can see exactly how useful it can be. So like I've said, a z-score specifies in units of standard deviation where an x is on a distribution. So I want you to take note of this entire definition. So the first thing is that you're going to use units of standard deviation. So that means that you're working only within your sample or population. So you're using the standard deviation that is specific to that group of people. Okay, so what you're really doing is comparing one raw score to everybody else in that group, right? So now we're just working with that specific distribution and not really worrying about a different group anywhere else. We're just dealing with this one group of people or scores. Now, like I said, a standard deviation is always positive. So I can have a distribution that has a mean of 100 and a standard deviation of 80. Right? But a standard deviation can't be negative because it's a distance measurement. So I'm saying with a standard deviation of 80 that on average scores are about 80 points away from 100, either in the positive direction or the negative direction. What a z-score does is it starts to tell us whether a score is higher or lower than the mean. So if you have a positive z-score, this means that that particular score, right, because what we're going to do is we're going to turn each raw score, each x, into a z. So we're going to have the raw score, and then we're going to have its complementary z-score. So if a raw score has a positive z associated with it, that means that the raw score is higher than the mean. If the z-score is negative for that particular x, then that means it's lower than the mean. Now, the positive and negative tells you whether it's higher or lower than the mean, and the size of that z indicates its distance from the mean. So if you have a large z-score, which we will define, you have an extreme score, all right? If you have a small z-score, that means your score is hanging around the mean, and it's not very extreme. So this is one usefulness of the z-score. It can quickly tell us where the extreme scores are, or whether a raw score is an extreme score. So like I said, people need a z-score of a 2.0 on any accepted intelligence test to qualify for Mensa. So a 2.0 is an extreme z-score. Only 2% of the population has that score on an intelligence test or higher. Right? So that's really what Mensa is saying. What Mensa is saying is we only accept the top 2% of intelligence test takers in the world, and that's their criteria. So a Z of a 2.0 or a negative 2.0 are actually really extreme scores. And I want you to keep this in mind because as you calculate a Z, I want you to think through the math as you do it. So what kind of z-score should I be getting? If you end up with a z-score of 8, then that's really, really, really extreme, and you might want to check your math and make sure that that's correct, right? So most z-scores are going to fall between -1 and 1. A lot of your z-scores, 95% of them, are going to fall between -2 and 2. So if you're getting something way outside of that when you calculate a z-score, there might be something incorrect in the calculations. Always check your calculations twice to make sure. So let's transform our raw scores into z-scores. Now keep in mind what we're doing is transforming one single raw score from our entire distribution into its corresponding z-score. Okay, so each raw score, or each x in your distribution, will have its own z-score. So when you're transforming a raw score into a z-score, what you're really asking is how many standard deviations away from the mean is the raw score? So again, we're working in units of standard deviation, and we are always comparing to the mean of its distribution. So the first thing that you're going to do is simply calculate the distance in whatever units it is that you used in the first place. So you're going to subtract the mean from the score. So here we have the mean, represented as mu, since in this example we'll be dealing with a population, and we're subtracting that from our x score. So we're just going to calculate the actual difference between those two numbers. And then we're going to divide by the standard deviation, in this case represented by sigma because we're dealing with a population. And that's it. So in order to calculate your z-score, you just need the raw score that you're converting, the mean of the population, and then you divide by your standard deviation. The resulting number gives you a z-score. So let's take the example that we just used for the International Smarty Test. So let's assume that you have a score, a raw score of 34. Your mu is 26. Your sigma is 4. In order to calculate your z-score, you simply subtract your mu from your x and divide by your sigma. So we have our 34, which was our raw score, our 26, which was our mean, and we divide by 4, which was our standard deviation. That gives us 8 divided by 4, which gives us a z-score of 2. So that's pretty much it. If you want to turn any raw score into a z-score, if you're comparing that raw score to its own distribution, that's how you do it. So when you get a z-score of 2, that tells you, oh, this score is actually pretty extreme, right? And so it gives you some information about that particular score. Now, the process is very similar for samples. So we're also going to subtract the mean from the score. Of course, this time we're representing the mean with m because it's a sample, and we're still going to divide by our standard deviation, in this case s because it's a sample. So again, your score is x. And if you want to figure out your mean, if all you have is your raw scores, of course we can use the equation for figuring that out, which is just the sum of x divided by n. If you still don't have your standard deviation, remember we can also figure that out. We just need to find the sum of squares first, then your variance, then your standard deviation. Now, this looks like a lot of formulas, and it is, but you've already learned most of them. The only thing that's new here is the z-score. Now, what this means is that if you have your entire distribution, if you know all of your raw scores, you can calculate all of this on your own. And the math isn't necessarily hard, it's just time consuming. And you have to make sure to stay organized. So when you're calculating your sum of x squared, remember you're going to square each one of your scores, and then you're going to sum those. And then you're also going to sum all of your scores and square that and divide by n. That's going to give you your sum of squares. In order to find your variance, you then divide by n minus 1 because this is a sample, and that gives you s squared, or your variance. Then you take that number and you take the square root, and that gives you your standard deviation. Again, lots of steps, so it can get a little confusing, but the math itself is not super hard. So once you find your standard deviation, we can then go back and plug it into our z-score formula. So when it comes to calculating z-scores, if you're working from just a set of raw numbers, it can take a little while, but once you have your standard deviation and your mean, you can find the z-score for any raw score in your distribution. So the hard part is just getting those two numbers. So let's do some practice. Okay, let's just jump right in. So participant number 1 and participant number 2 are both participants in a study about health behaviors. Researchers collected various data to come up with one score to represent each person's health. So you can imagine maybe they took how much they smoke, or how much they exercise, how much they sleep, how well they feel. All of those things together came together to form one number that's an indicator of their health. The mean health score on this overall measure was 84.2, and the standard deviation was 26.1. So I've given you the mean, and I've given you the standard deviation. So if you wanted to find any z-score, you could, as long as you have the raw score. So remember, in order to find a z-score, we just need the raw score, the mean, which I gave you, and the standard deviation, which I also gave you. So if participant number 1 scored a 48 on this particular health measure, what was their z-score? So I recommend pausing here and trying to do the math on your own and coming up with a z-score. So what did you get? Hopefully you did it like this. Your z-score is, again, score minus mean over standard deviation. Our score is 48. You subtract 84.2 and you divide that resulting number by 26.1. That gives you a z-score of negative 1.387. Now, is this an extreme score? Not really. It's still within 2 standard deviations, kind of close to 1 standard deviation away from the mean. But what we do know is that their health is not great, right? It's below the mean. So their health is relatively poor, but not so poor that we might be very concerned about this person. Participant 2 has a z-score of 0.45. What is their original score on that health measure? So this is a little bit of a curveball, but I want you to see that if you have a z-score and you have a mean, which I gave you, and you have a standard deviation, which I gave you, you can solve for x. Oh, is this bringing back memories of algebra? So you just need to get x alone, and then that will give you their original score. So we can either compute z-scores from raw scores, or we can compute raw scores from z-scores. So I want you to just take a second to try and figure out what the raw score is for participant number 2. So what did you get? So I am the kind of person who likes to solve for the variables first. So what I simply did was multiply both sides by standard deviation and then add my mean to both sides. This means that in order to find the raw score, I simply take the z-score that they gave me, multiply by my standard deviations here, and then add my mean, which is here. So what that gives me is 0.45, right, my z-score, multiplied by my standard deviation of 26.1. And then to that number, I add 84.2. And this gives me a health measure of 95.945. And this makes sense because the z-score means it's about half a standard deviation away in the positive direction, right? So I'm looking for a raw score higher than the mean because the z-score is positive, but not a lot higher than the mean. So 95.945 makes sense given the z-score that we got. Now let's take a second to go back to our normal curve. As you remember from the beginning of this lecture, the middle is going to be our mean, and then we'll have one standard deviation away to the right and to the another standard deviation away to the right, and we have the same on the other side. Now, I want you to think about the normal curve in terms of the z-scores of all of the scores that make up this particular distribution. So let's say we have a score here that's going to have its corresponding z-score as well as all of the scores, right? So we could potentially get the z-score for every single raw score in our distribution. And that would make up the z distribution, okay? So the z distribution is basically a distribution made up of all of the z-scores in any normal distribution. Now, if you make z-scores for all of the raw scores, the distribution of z-scores will have the same shape as the original distribution. And this makes sense, right? The z-scores aren't changing anything about how far away the scores are from the mean. We're just saying it in a slightly different way, in units of standard deviation. And if you were to take the mean of your distribution and convert that into a z-score, that would make a 0. And that's because you would be taking the mean from the mean and dividing by your standard deviation, but it doesn't matter because your mean minus your mean would equal 0. So your mean always has a z-score of 0 is the point of that little formula there. And we know that a standard deviation, one standard deviation away, is a z-score of 1. So that means when you have a z-score of 1, the x score, or the raw score associated with it, is one standard deviation away from the mean. So if we think about it again, instead of this graph, we have a z distribution where our mean has a z of 0. And at every point of a standard deviation away, we have another z-score. So here, at one standard deviation away, our z-score is 1. Over here, our z-score is -1. And then finally, over here we have a z-score of 2 and a z-score of -2. Now, if you remember, this means that we have an interval scale. So that means that our 0 is not super meaningful. It just happens to be what the mean is. And then we can also have negative numbers, which means that we have an interval scale. Now, right now, this z-distribution may not be that thrilling and exciting to you, but the z-score distribution is going to be very helpful when we start to calculate some other statistics based on the z-distribution. So just keep this in mind, and we will definitely come back to it later in the course to help you figure out some stuff about your distribution. So that's it for the lecture on z-scores. I hope that you appreciate the value of them and see that we can now compare apples to oranges. And in the next video, we'll go over some practice so that you can get used to computing your RAS scores, your z-scores, etc. And you'll see exactly how the magic happens. Thanks for listening, everybody.